As we know the formation of the dew and frost, now we'll be talking a very interesting things that the condensation nuclei and droplet forming. So actually the condensation process that produce cloud is not so quite simple that we think about. Just dew and frost need a surface to form on. There must be airborne particle on which water vapor can be condensed to produce cloud droplets. Although the air may look like very clean, it's actually never very clean. On an ordinary day, a volume of air about the size of our index finger contain between 1000 to 150,000 very, very small tiny particles. Because many of these serves as a surfaces on which water vapor can condense. That particles we will call here the condensation nuclei. Without them, without the condensation nuclei, relative humidities of several hundreds% would be required before the condensation could begin. So what are the size of this condensation nuclei? Some condensation nuclei are quite small and have a radius of less than zero point 0.1 micrometer. Particles ranging in size from 0.1 to 1 micrometer called large nuclei, while other called bigger than that called giant nuclei. The condensation nuclei most favorable for producing cloud, we call it cloud condensation nuclei, have the radius of 0.1 micrometer to little more. Between 100 and 1000 nuclei of this size can exist in a simply a cubic centimeter of air. These particles enter the atmosphere in varieties of ways, such as the way of dust and volcanic ashes, factory smoke, forest fire, salt from the ocean spray, and even sulfate particles emitted by phytoplankton in the ocean. Most particles are released in the atmosphere near the ground. The largest concentration of these condensation nuclei are observed in the lower atmosphere near the Earth's surface. What is the weight, the mass of these nuclei? The condensation nuclei are extremely light, so it's maybe a mass of less than a 1 trillionth of a gram, very, very tiny. So they can remain suspended into the air for many, many days. They are most abundant over the industrial cities, where highly polluted air may contain nearly 1 million particles per cubic centimeter. So this condensation nuclei decreases in, in the content where the clean air, such as countryside, also over the ocean too. So nature of these condensation nuclei, some particles are hygroscopic. Hygroscopic mean water seeking, and water vapor condenses upon these surfaces when relative humidity is considerably lower than 100%. So ocean salt is hygroscopic, as it common table salt. In humid weather, we know that it is difficult to pour salt from the shaker because water vapor condenses onto the salt crystal, sticking them together. Other hygroscopic nuclei include sulfuric and nitric acid particles, but not all the particles are actually water-seeking or hygroscopic. Some are not. Some are hydrophobic, that we could call water repelling, such as particles of oil, gasoline, paraffin waxes. These particles resist condensation even when the relative humidity is above 100%. As we can see, condensation may begin on some particle when the relative humidity is well below 100%, and on the other hand, only when relative humidity is much higher than 100%. So briefly, we can understand from here that if we have the condensation nuclei is actually thousands times bigger than the water molecule. So when its surface attraction of the condensation nuclei, the water molecule gather around the condensation nuclei, and then it's become bigger, and then the more condensation nuclei stick together due to surface tension attached together, and it's become bigger, bigger, bigger. When it is such a bigger portions like 1 millimeter in diameter of this droplet, that is through that gravitational pull to the ground, it cannot be suspended into the air. So it's drop as a droplet. Then we can see rainfall, snowfall. Okay, that's the thing. So we know condensation nuclei.